record and share my screen. And what I want to do first is look at that homework that is due November 4th, which is next week, Wednesday. I had said that the first 2 pages we had covered last class, and also that homework from chapter 3. When I graded them, if your papers were submitted in Blackboard, you should be able to see the graded work. If they were submitted otherwise, if you want to see the graded work, send me an email and I'll see. There's some files that I just cannot annotate. There are some files that won't let me write on them. And so those ones, I haven't been able to write on the paper to give back for every assignment, but I do keep a running total of your grade as I go through. Does anybody want to look at any problems? Did anybody start looking at the work on page 94 or page 203? And you have problems, just with what the question was asking? Okay, I guess I'm going to take that as a no. And so last class, we left off with these tests for divisibility, and we looked at the tests for divisibility. We have tests for divisibility by 2, 4, 8, 5, 10, 3, 6, 9. 7 and 11 and 13 used to be in the old textbook, but honestly, when it came to those tests in the old textbook, I always said the tests were so involved that it was probably just easier to try to do the division. I did leave this extra page in though, because I'd like to look at the idea of checking divisibility with manipulatives. And so let's say I want to show that 9 is divisible by 3. What I could do is take my 9 rod and then show that if I lined it up, it would match up exactly with 3 blocks of 3. So this would be the strip for the number 9, and we could show that it's equal to 3 for the number 3. So in the same way, we could use those to answer a question for a young child, like, is 10 divisible by, let's say, 4? Well, I could take a strip that's 10 long, and if I start comparing it with strips of length 4, there's 1, there's 2, and then, oh, if I will go for a third one, it's too long. And so would this arrangement show a child that no, 10 is not divisible by 4? Does that all make sense, folks? And just see if you can line up an even number of the smaller number strips to get to the larger ones. So if that's all right, when we look at divisibility, can I turn the page? Yeah. When you look at divisibility, one thing that you hear is the greatest common divisor. The greatest common divisor of two numbers, let's say lowercase a and b, the authors of the textbook write it as, so we'll say is written by G, C, D, greatest common divisor of A and B. And the greatest common divisor, also called, this would be the greatest common factor, there's one and the same, is the largest number that divides both evenly. And so we're looking for the largest number that can go into both numbers. Now we had said, we're going to say that two numbers are relatively prime if the greatest common divisor of the numbers is 1. So for example, if I look for the greatest common divisor of, let's say 5 and 13. This is asking, what is there a number that divides both 5 and 13 evenly? Well, if I make a factor tree, the only divisors of 5 are 1 and 5. If I make a factor tree, the only divisors of 13 are 1 and 13. So the largest number that divides them both is 1. So we say that 5 and 13 are relatively prime. There's a couple of different ways that the authors of the textbook go and ask you to find the greatest common divisor of two numbers. And one is to take the intersection of their sets. To do this, what we want to do is we want to find the set of all the divisors of each number. So let's say, for example, I want the greatest common divisor of 24 and 54. So let's first list the divisors of 24 as a set. So help, what numbers go into 24 evenly? I'll do the hard one. 1,
2,
2,
6,
4,
6. What else?
12,
3,
12, 3,
4,
4. What else?
8,
8.
8,
What else?
can we even say 1?
Yep, we got 1 in there already.
Oh, I can't see. I thought that was 12. Oh, we got 12. Okay.
9,
Does 9 divide 24 evenly?
To go with 24, but 54, yes, but not 24.
Right. How about 24 though? Doesn't 24 divide 24 evenly?
Yes.
I think that's it. So now let's list the divisors of 54. 1. I think 2 goes in there, right? Does 3 go in there?
It should be able to by both of them ending with 4. It should be able to.
3 should, because remember we had said 5 plus 4 is 9, and 3 goes into 9 evenly.
6.
6. 9.
No.
No. Let's look and see. What number do we multiply 6 by to get 54?
Oh, yeah. Yes, ma'am.
9,
Okay, what number would we multiply by 3 to get 54? If we were going to take 54 and divide it by 3, what would we get?
18,
18.
18,
What number, how many times does 2 go into 54?
27,
27. And how many times does 1 go into 54? 54. So now what we want to do is we want to look at the intersection of the two sets. And remember, the intersection is what they have in common. See, they both have 1. They both have 2. They both have 3. They both have 6. Anything else that's common to both of them?
no,
I can't see anything else.
So the greatest common divisor, the largest one in that set would be 6. And so I guess that method of finding that the greatest common divisor kind of goes back to the definition, yes? Let's go through, let's find the divisors of both numbers. Let's see which ones they share, what's in their intersection. And then we want the greatest of those. Everybody all right with that?
yes,
Yeah, except I'm going to tell you that I'm a little bit lazy. Shh. I know there's some on the homework that ask you to do that, but I think there's got to be a quicker way. And so the one other way of doing is to find the prime power factorization of each. So we're going to compare the prime power factorization of each. And if I remember correctly, in order to find that prime power factorization, last class we had 2 ways. Should we do 24 one way and 54 the other, just so that we practice both ways? For 24, let's make a factor tree. Can anybody think of numbers that go into 24 evenly?
12 and 2,
12 and 2. Let's see, can you think of numbers that go into 12 evenly?
4 and 3.
4 and 3. Can you think of numbers that go into 4 evenly?
2 and 2.
2 and 2. Say 2 is prime, 2 is prime, 3 is prime, 2 is prime. So we can say that 24 is 2 to the third times 3. With me so far? And then the other way we had of finding that prime factorization was what we called short division. And I know some of you weren't real pleased with that, but I'm going to do this number that way just so we practice. It's an even number, so it's divisible by 2. 2 into 54, we said, was 27. 2 doesn't go in there anymore, but 3 does. 3 goes into 27 9 times. 9 isn't prime. We can divide it by 3 again, and we get 3. And so our prime factors are 2, 3, 3, 3. So 54 is 2 to the first times 3 to the third. For the GCF, we use the lowest exponent on any common factors. So the greatest common divisor, or the greatest common factor of 24 and 54, well, when I look at their prime power factorizations, they both have factors of 2 and 3. What's the lowest exponent on 2?
1.
1, beautiful. What's the lowest exponent on 3?
3.
What's the exponent on this 3?
1.
Isn't the lowest exponent on 3 also 1? And so the greatest common divisor is 2 times 3, or 6. So using that method, I'm going to shut up and ask you folks to please find the greatest common divisor of, let's say, 72 and 48. And I'm going to be quiet and give you a minute or two to work on that. How's it going? Does anybody have the prime power factorization of 72? Did anybody make a factor tree for 72 and list its factors with exponents? We still working on it? Or are you guys just too scared to volunteer?
Yeah, something like that.
Okay, well then I'm gonna ask you to recreate the work then. What did you get to multiply? Did you do a factor tree or short division?
I did a factor tree.
Okay, what did you say went into 72?
36 and 2.
Okay, two's prime. We got
3 and 20. I'm
36.
sorry. 3 and 24.
Oh, you used 3. Okay, so you made the list of factors and compared them.
Yes, ma'am.
Okay, can we instead look at this prime factorization method first and then look at comparing the two intersection of sets?
Okay.
Factor tree people, what did you do with 36?
18 and 2.
18 and 2. And what did you do with 18?
3 and 6.
And what did you do with 6?
2 and 3.
2 and 3.
So we've got 3 2s and 2 3s. That one all right? How about 48?
6 and 8.
16 and 3.
6 and 8. I heard 6 and 8 first, so we'll look at the 16 and 3 later. It should take you to the same place. 6 is 2 times 3. How about 8?
4 and 2.
4 and 2. And 4 is 2 and 2. So what do we have here? We have 1, 2, 3, 4 2s.
Yes.
1 3.
Yes. So is it correct if I say 3 times 2 to the 4th power?
I like where you're going. Oh, that's what 48 is equal to. But for common factors, we've got a 3. The lowest exponent is 1. They both have 2s, but
Yes.
between them, what's the lowest exponent on 2?
3.
3. And so that becomes 3 times 8, or 24, is the greatest common factor. Now, I think, Dorothea, it was you that said you looked at the intersection method instead?
I believe I did.
And so you said for 72, you started, that's 1 times 72, 2 times 36. You said that was 3 times 24. I think it's also 4 times 18.
Yeah.
And
9 and 8.
9 times 8 and 6 times 12.
Yes.
Is that it? Let's see. Remember last class we said one way of finding out the total number is to take those exponents and add 1, which would tell me that I should have 4 times 3 or 12 factors. Let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yay, we got them all.
Mhm.
Now 48, let's see, if I look at the exponents, I should have 5 times 2 or 10 factors of 48. So let's see, I'll do the hard ones. 1 times 48. I think 2 times 24. I think you said 3 times 16.
Yes, 3 times 16.
And 4 times 12. And that's 1, 2, 3, 4, 5, 6, 7, 8. So I think we're missing some. Oh, 6 times 8, right?
Yes.
And so that's all 10. So now if we look at the intersection, what do both sets have in common? They both have 1. They both have 2. They both have 3. They both have 4. They both have 6. They
Mhm.
both have 8. And they both have 12.
Yes.
And they both have 24. What's the largest number in the intersection?
24.
And do you see how both methods took us to the same place? Which is the best method? I guess it depends on the size of the numbers that you're looking at. There's a third method that initially seems a bit more involved than the others, but it would be much easier to use if we had very large numbers. And so that third method of finding the greatest common denominator is something that's called, can I turn the page?
Yes.
Is something that's called the Euclidean algorithm. And it says if A is equal to B times Q plus R, the greatest common divisor of A and B will equal the greatest common divisor of B and R. What's that all about? What we're going to do is we're going to say to find the greatest common divisor of two numbers. Every once in a while, my hand doesn't work. I apologize. Two numbers. The first thing we're going to do is we're going to divide the larger by the smaller. So before we were looking for the greatest common divisor, let's look for the greatest common divisor of 24 and 54. So we'll take 54 and divide it by 24. I think the closest we can get is 2. 2 times 24 is 48. And when I subtract, I have a remainder of 6.
Yes.
Now what we're going to do is we're going to divide the first divisor by the remainder. So we're going to take that 24 and divide it by 6. Well, 24 divided by 6 is 4.
4. Mm-hmm.
And we're going to repeat that process till we get a remainder of 0, which we just did. The greatest common divisor is the last number we divided by. So that would tell me the last number I divided by that gave me a remainder of 0 was 6. So the greatest common divisor of 24 and 54 is 6. How cool is that one?
Yeah.
So let's try another one using that method. Let's find the greatest common divisor of 363. And I apologize, I shouldn't have written the word and in there. I should have put a comma. 363 and 77. So we'll take 363 and divide it by 77. I think 5 would be too big. So let's try 4. 4 times 7 is 28. Carry the 2. 4 times 7 is 28 with that other 2 is 30. And so when I subtract, I get a remainder of 55. Now we're going to take the 77 and divide it by that remainder. How many times would 55 go into 77?
Once.
Once. And what would my remainder be?
22.
Definitely not 0, right? So
Right.
let's take that 55 and divide it by the last remainder. How many times does 22 go into 55?
Once. Oh,
Twice.
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 Twice would give me 44, and my
Yes.
remainder is
11.
11. Definitely not 0. So I'll take that 22 and divide it by 11, which gives me
0.
a remainder of 0, right?
Oh, I'm sorry. 22. I got 2 ahead of myself.
Yeah, I knew what you meant. So since our remainder is 0, we'll say that the greatest common divisor is 11.
Wow.
Again, if I were looking at very, very, very large numbers, if I were looking at, numbers in the thousands, I don't think I'd want to list all the factors. I could probably make a factor tree, but I think if our numbers were large enough, this method would probably be a little bit more concise than the others. Can everybody wrap their mind around the process that we did to get there? Yep. Great. If so, after we've conquered that greatest common divisor, can I turn the page or are we still working, folks?
Yeah.
No.
The next thing we want to do is look for the LCM, which is the lowest common multiple of two numbers. We'll say the LCM of A and B is the smallest number that can be divided by both A and B evenly. In order to find the least common multiple, this time, instead of looking for the biggest number that goes into both of them, I'm looking for the smallest number that both of them can go into. We're going to have methods of finding them that kind of correspond to the methods that we have of finding the divisors. Just like the divisors had an intersection of sets, we're going to have an intersection of sets. We're going to compare the sets of multiples of each. The first common multiple would be the LCM. So I'm going to be a little bit lazy and use those two numbers that we've been beating the bush with and try to find the least common multiple of 24 and 54. So first I want the multiples of 24. So let me see. For my multiples of 24, 24 times 1 is 24. 24 times 2 would be 48. 24 times 3 would be 72. 24 times 4, 96. 24 times 5. Anybody want to help me with that one?
120.
120.
Mhm.
24 times 6.
144.
24 times 7.
168.
24 times 8.
192.
24 times 9.
216.
And I'll do the hard one. 24 times 10 would be 240. And
Yep.
that list can go on. Let's see if we went far enough. If I look for the multiples of 54, 54 times 1 is 54. 54 times 2 is 108. 54 times 3,
162.
162. Beautiful. 54 times 4.
216.
Does anybody notice anything?
Did I say two? Oh, 216 is the high. Okay.
Yeah, do you see?
the lowest.
Bing, 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 we got a winner.
It's the lowest. Okay.
So we'll say that the least common multiple of 24 and 54 is 216. That method, all right.
Yes.
We can also find the least common multiple by looking at the prime power factorization. To find the least common multiple using the prime power factorization, it's the product of all the factors, not just the common ones, but all the factors. And we use the highest exponent on any common factors. So if we're looking for the lowest common multiple of 24 and 54 this way, we had said that 24 was 3 times 2 to the third. And we said that 54 was 3 to the third times 2.
Mhm.
Is everybody right if I recycle those answers from last time around?
Gracie, are you a skater, dude?
So I'm going to take, as I look at those lists, I only see factors of 2 and 3. I want to use all of those factors. But this time I want to use the highest exponents. The highest exponent on 2 is 3. The highest exponent on 3 is 3. And so when I multiply that out, 2 to the third is 8. 3 to the third is 27. And when I take 8 times 27, let's see, 8 times 7 is 56. 8 times 2 is 16 plus the 5. It would take me to that 216. So seeing those methods both done out, I'm going to ask for the lowest common multiple of, I have to cheat a little bit. What numbers did we use before? We used 72 and 48. And so I hope you guys don't mind. We did that prime factorization before. Are you guys all right if we recycle it?
Mhm. Yes.
And so what factors do we see? I see 2, I see 3. The highest exponent on 2 is
4,
the highest exponent on 3 is
2,
2. So this is going to be 2 to the fourth is 16. 3 to the second is 9. And when I take 16 times 9, I get 144. If we have that prime factorization, is that easier than making our list of multiples? Yes? So third method that we have says if I have two numbers, A and B, the product of A and B is equal to the product of their greatest common divisor times their lowest common multiple. So the product of two numbers oh Lord. I just changed the battery in one of these styluses thinking that was why it wasn't working, but that's not helping. Equals the product of their least common multiple and their greatest common divisor. And so let's use this to find the least common multiple of 77 and 363. Well, first, we want to take 77 and multiply it by 363. So let's see, 363 times 77. 42 and 2 is 44. 21 and 4 is 25. Gives us 27,941. And I said 41 and I meant 51. We said the least common multiple of 77 and 363 was 11. So we're going to say that 27,951 is equal to 11 times whatever the greatest common divisor is. So to solve this equation, let's divide both sides by 11. So when I take that 27951 and divide it by 11, oh Lord.
Yeah, what do you gotta do? Bring down the 9 and then,
Yeah, my pen just stopped working. That's what happened there. The stylus wasn't writing on the surface. I apologize. 11 into 59 would be
5.
45 would be
Excuse me.
4. 11 into 11 is 1.
Yes.
So we'll say that I have to apologize. The 11 is the greatest common divisor. This should have been the least common multiple. Right? 11 was the greatest common divisor. So the least common multiple is 2541. What do you think? I don't think I would want to start listing multiples of 77 until I got to 2,541, would you? And so while this seems harried, I think it's shorter than going through and listing the multiples. I guess we could have gone through and made the factor trees for all of them. Should we try the prime power factorization method for these? What would the factor tree for 77 look like?
11 and 7.
And oh crap, they're both prime, aren't they? So let's
Yeah.
try 363. What would the factor tree for 363 look like? What goes into that evenly? Any ideas? I don't think 2 does. Do you think 3 does?
3 and 121.
3 and 121. I like it. Oh dear. Now, does anybody recognize 121?
Square root.
Yeah. 11 times 11 or something like that.
Something like that. You're good. 11 times 11. So prime factorization, 77 is 7 times 11. 363 is 3 times 11 to the second. So I guess using this method for the least common multiple, I think the only thing they share is 11 and the common exponent is 1. No, you guys, why did I do that again? I think this is called being sleep deprived. That's the greatest common divisor, isn't it? The least common multiple, we have to list all of the factors. So between all of those numbers, the factors I see are 3, 7, and 11. The highest factor on 3 is 1. I'm sorry, the highest exponent on 3 is 1. The highest exponent on 7 is 1. What's the highest exponent on 11?
2.
2. And so that would be 21 times 121. Gives me 2541. And that's the same answer we got the other way. So do you see how we've got different methods for doing these? Huh. And guess what? That's the end of the chapter 5 notes. If you look at that third page, I'm sorry, chapter 4 notes. Hello. I'm just misspeaking today. I apologize, folks. That's the end of the chapter 4 notes. If you look at that third page of chapter 4 homework, all of the questions involve either finding the lowest common multiple or the greatest common divisor. Some of them are word problems. Take your time looking at them. If you have questions on them, please ask. We can look at them next class or during my office hour. What I'd like to do with it's only 7 o'clock, I don't think I'm going to take the entire class time today because I don't want to delve too far into the next chapter. But I know that you folks said last week that you enjoyed looking at some of the activities before we started the chapter. And so what I did was I included in here the 3 activities from chapter 5. And so I thought that we'd look at those 3 activities from chapter 5. And then, shall we call it a night after that and end a little bit early today? Would that be all right with everybody?
Yes.
Yes.
Okay.
Yes.
I didn't think I'd run into too much objections to that. I always hate it when I end classes way too early, though, because I feel like I'm not giving you folks your tuition's worth. Will you forgive me? Okay. So activity 5.3. Well, before we do that, I guess we should talk a little bit about what chapter 5 involves. Chapter 5 starts talking about adding to the discussion the idea of negative numbers. And so in looking at chapter 5, we're looking for ways of explaining positive and negative numbers to elementary children. And I think this activity 3 in chapter 5 works with a clown on a tightrope. And I think it's great fun. If we were on campus, I would have made a transparent clown for everybody to have their own. But because we don't have that, we're going to have to wing it a little bit. We're going to develop rules for addition and subtraction of integers. By integers, what we're referring to are our signed numbers, our positives and negatives, using a number line model. They say the material that we need is a transparency of the clown on the left, but I apologize, I'm not a good drawer, but we're going to try to wing it in terms of what he looks like. You're going to, let's start setting them up together and then give everybody a few minutes to work on some of them on their own. The clown performs on his tightrope act, and the tightrope is going to be a number line. He starts each act standing on the first number. For addition, the clown faces to the right. So this would be an addition clown. My clown pictures are going to be kind of sucky. There's my clown facing to the right. For subtract, and I should have drawn that up here. Subtraction, instead he's going to face the other direction. So he'll be facing towards the left if we subtract. For a positive second number, he's going to walk forward. For a negative second number, he's going to walk backwards. And so let's look at this example. This example says, I want to see what happens if I take 1 minus -4. So he starts at the number 1. Because it's subtracting, he's facing to the left. And because it's negative, he goes back 4. And it takes him to the number 5. So what does 1 minus -4 equal? 5. So I guess in order to do this, I'm going to insert another page. And well, I don't have room here, so I'm going to have to insert another page after this. The next one that we're looking at is 2 plus 3. So on our number line, we're going to start with our clown on 2. Because we're adding, he's going to face to the right. Because that 3 is positive, he's going to move forward 3. 1, 2, 3. And we get 2 plus 3 is 5. The sheet asks you to try to draw similar pictures for these others. Let's look at, should we just look at, oh, let's look at all of them. So I'm going to leave this up for a minute, and I'm going to ask you all to take a minute and draw your clown pictures for 3 plus -5, for -4 plus -2, for -7 plus 9, 3 minus 7, 6 minus -2, -5 minus 3, 3 minus -6, -2 minus -4, -5 plus 3 minus -8, and 2 minus -7 plus -12, and -9 minus -11 minus -7. And so could you folks try to draw your clown pictures to come up with answers for each of these? Do you folks need to still see the problems on the screen, or did you write them down? Or do you have your own activity sheets?
I'm writing down the problems that I see here.
Okay, let me know when you're done, because then I'm going to stop sharing my screen for a few minutes and let you folks work on those. And the bad artist that I am, I'm going to try to draw these out too. Does everybody have them all?
Well, I'm on number 10. Well, actually, I'm starting at number 11 right now.
Writing it down or doing it out?
Doing everything out.
Okay, all right.
Yes.
Yes, what? You got them all done?
I haven't did these in a while that I'm really stuck on number 11. I can't believe it.
Well, are you doing it with the clown or are you just doing the arithmetic?
I was just doing it arithmetically.
I was trying to do it with a clown. So number 11 was the one that started with -5.
Okay. So he's facing the left. Okay.
Well, let's look at it and see. He's starting on the first number. So on this number line, he's going to start at -5. And we're adding. When we add, he faces right. And it's a +3, so we'll go forward 3. 1, 2, 3. So that takes us here. Now
To the -2.
we're subtracting. So he's going to turn around
10.
because it's subtraction. And it's a -8. So now he's going to go backwards 8. 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And that takes us here,
10.
+6. What do you think of the clown way of doing it? Should we do some more?
Oh, well. Oh, boy.
I'm just going to pull some random ones out. 6 minus -2.
That'll be 8.
So my clown's going to start on 6. I'm subtracting. So he's going to face left. And it's a -2. So he's going to go backwards 2. And so our final answer is 8. What do you folks think of this clown method?
I like the clown method.
It's something that kids might enjoy. Does anybody, anyone in particular that anybody wants to go over besides 11? Should we look at those the last two, or should we go over all of them quickly, or what do you guys want to do?
We can go, well, I think the last two, because those were my toughest ones, but if I followed your clown routine or your clown method, I think I probably would have got them correct. But
Well, let's do it with the clown now. The next one was 2 minus -7 plus -12. So because this is we're going to start on 2. Because it's subtraction, he's going to face left. Because it's negative, he's going to go forward or backwards. Negative is backwards. 7. 1, 2, 3, 4, 5, 6, 7. And so that takes him to here. Once he gets here, we're going to add. When we add, we face right. But we're adding not 12, but -12. So from
yes,
here, we're going to go backwards 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, I actually drew that the right length, winging it. And so that takes me to -3. What do you think?
yeah, I think that was easy. I remember when I first learned how to do these, of course, it was when I was a child, but I didn't remember that. It took me a while to get back to school. But when I finally made it to school, they looked at it as somebody owing someone money. So
Right.
I understood it really well when they did it like that. Like -7 means you owe me $7. -12 means you owe me $12. So I really understand it. And I see that right there, that 2 take away -7. I remember if they have the same sign, you change it to positive. So that's what I did. I said 2 plus 7 would be 9. And then that 12, that -12, okay, so but you still owe me 12 and I only have $9. So you still owe me $3. So I like how the clown methods. Like I really understand it better now because I understood it with money and now I understand it with the clown um, um, method. So
Well, should we see what the rest of the clown sheet then says? Is everybody else all right with this? Do you think it's something you might want to do with children? Let's see.
yes,
So all of our answers were 5. What did you folks get for 3 plus -5?
-2,
Beautiful. -4 plus -2.
-6,
Beautiful. -7 plus 9.
+2,
+2. Beautiful. 3 minus 7.
-4.
-4. Beautiful. 6 minus -2.
8,
8. Beautiful. -5 minus 3.
-8,
-8.
Beautiful. 3 minus -6.
9,
9. -2 minus -4.
-2, or
Let's see.
just 2.
We're starting at 2. We're subtracting, so he's facing left. His nose tells me which way he's facing because I can't draw. It's a -4, so I'm going to go backwards 4. 1, 2, 3, 4. And so doesn't that take my sorry looking backwards clown to +2?
Right.
And let's see, -5 plus 3 minus -8, I think we said was 6. 2 minus -7 plus -12, I think we said was -3. And oh my heavens, what are you guys getting for -9 minus -11 minus -7? Should we do that one with a clown, or do you folks have an answer for me? So we're starting on -9. We're facing left because it's subtraction. We're going backwards 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that takes us here. And then we're still subtracting. So we're still facing backwards. Facing left, and we're going -7, backwards 7. 1, 2, 3, 4, 5, 6, 7. And so first we're going backwards 11, then we're going backwards 7. And so I think that takes us to +9. So is the sum of 2 negative integers positive or negative? When you added 2 negative numbers,
Positive.
when I took a negative number and added a negative number, let's see, that would be like number 4, right? Negative plus negative is negative.
Negative.
How can you find sum of 2 negative integers without using number line? We had said that -2 plus -4 equals -6. Without using that clown on the number line, how could you have done it?
Thinking about money, somebody came to borrow $2, then they came back to borrow $4.
Okay. We can think of money, borrowing twice. Anybody else have another way we could do it?
like they were really confusing me when they were like, a bad person in a bad neighborhood is bad. A good person in a neighborhood, a good person in a bad neighborhood. I was like, wait a minute. So when a student stood up and said, I look at it as money, that's what helped me because I couldn't do it with a negative person in a negative town and all this stuff. Do you remember that, Mrs. Christie?
No, I don't remember. I don't know that I've ever heard that one. I'm kind of looking more like this. If they're both negative, can I just add the absolute values? 2 plus 4 is 6 and
Oh,
make it
yeah.
negative?
Oh, yeah.
Now, when is the sum of a positive and a negative positive? Let's see, when we add a positive and a negative and we got a positive, I think that would be like number 5. When we add a positive and a negative, I think that's the only one. Ooh, I moved that and only some of it moved. Something weird happened there. When we add a positive and negative and get the positive, doesn't that occur when the positive number has the greater absolute value?
Mhm.
When is that sum negative? See, when did we have the sum of a positive and a negative being negative? I think, and this example was -7 plus 9 was 2. I think the sum of positive and negative being negative was 3 plus -5 is -2. What could we say about that?
Well, like I would just say the opposite of what you put down for positive. Negative has less absolute value or
Well,
has
the negative would have the larger absolute value, right? Because 5 is bigger than 3.
oh, larger. Okay.
When would they equal to 0?
When they're the same,
When they have the same absolute value.
like a -4 plus a negative, wait a minute, like a -4 plus a +4. So if you owe me $4 and you give me $4, you no longer owe me money.
Beautiful. So if I have a positive and a negative number, to find it without the number line model and to find it without the signs, can't we say I used to see it as if the signs are different, I take the difference of the absolute values.
Or can someone say if if the signs are the same, you add, and if they're different, you subtract, something like that?
Yeah. Or what always stuck with me was rather than saying if they're different, subtract. In my mind, if they're different, take the difference, because take the difference is subtracting. And so it always stuck with me that they, if you want to say subtract instead, you can. And we're going to use the sign of the larger value, larger absolute value. And so, for example, if I had -8 plus 5, the signs are different.
-3.
The difference between 8 and 5 is 3, and we'll take the negative because 8 is larger than 5.
And I looked at that, there's that money sign again. If you owe me $8 and you give me 5, you still owe me 3.
Beautiful. What if instead I had 12 plus -4?
Okay, so I will look at that as I have $12. You want to borrow 4. So I just got confused right there.
Well, let's look at what's the difference between 12 and 4. 12 minus 4 is
8.
8, and 12's positive. 12 is bigger, so it's +8.
Oh, okay.
So if I have $12
Yes.
and somebody sends me a bill for $4,
Yes.
all I have left is 8.
Okay.
Okay,
Yes, thank you.
so this worksheet, all right.
Yes.
Okay, so then the next worksheet asks you to explore patterns to develop rules for subtracting integers. And so let's look and see if we can find some patterns here. 4 minus 0 is 4. 4 minus 1 is 3. 4 minus 2 would be. This is the next one. This is activity 5.4.
My numbers on my sheet aren't matching up with your numbers.
On activity 5.4?
Mm-hmm.
Mine are multiplications, not subtraction.
Oh dear. Let me look and see what I meant for you to have then. I scanned these in. Okay. So for you guys, the clown was 5.4, 4, and the subtraction patterns is actually 5.3. So what happened there? So can you look in your activity manuals on page 81 at activity 3? Now do your numbers match up?
Yes.
Okay, so this is, I'm gonna change this one to activity 3. And I'm gonna change this one to activity 4, and I apologize for that. And so can you folks try to fill in these first 4? And see what you notice.
I get all the patterns. I see all the patterns. Which one are we to do?
You're supposed to fill in all of this 1, 2, 3, 4. It's in
Okay.
your activity manual on page 81. How did I do? Are you folks getting the same results as I and the same patterns?
Mhm.
So now, the next part asks us to, next to each of those subtraction problems, write a related addition problem using numbers that have the same absolute value as those in the problem. Huh. So over here, where I'm going to try to make this a little bit bigger, so I have a little bit more writing room because I am elephant printing today. Over here, 4 minus 0 is 4. That be 4 plus 0 is 4. Four minus 1 is 3. Huh. What would I add to 4 to get 3?
-1.
-1. Beautiful. 4 minus 2 is 2. What would I?
-2.
-2. 4 minus 3 is 1. What would I add to 4 to get 1?
-3.
-3. What would the next one be? What would I add to 4 to get 0?
A -4.
And how about the next one? What would we add to 4 to get -1?
A
-5.
-5.
What would I add to 4 to get -2?
-6.
-6. Now, let's look at the patterns to the right, question number 2. What would my pen does not want to write today. What would you know what I think happened? I'm going to try to move that for a minute. There we go. That's what happened. What would I, or not? Okay, you guys can write. I can't. What would I add to 3? There we go. To get -1. Would that be -4? What would I add to 2 to get -2? -4. What would I add to 1 to get -3?
-4.
-4. And so we see the pattern there. How about with number 3? What would I add to 4 to get 1?
-3.
Beautiful. What would I add to 4 to get 2?
-2.
What would I add to 4 to get 3?
-1.
-1. What would I add to 4 to get 4?
0. Yeah, Play-Doh 0.
What would I add to 4 to get 5?
1.
1. What would I add to 4 to get 6?
2.
2. And then patterns for number 4. What would I add to -4 to get -7?
-3.
What would I add to -4 to get -6?
-2.
-2. And what do you notice about each and every one of these?
The sign just switched.
And so can we say to subtract integers, what happens? We keep the first one the same. The subtraction becomes addition. And then don't we take the opposite of the second number? Or to subtract, you add the opposite.
I also learned to stay flip switch.
Yep, that's exactly what we're saying here. First one stays, second one is the opposite, and then we switch.
Oh, so that's that term where they say keep change, flip.
Keep change flip is actually more with multiplying fractions, because we're not
Okay.
really flipping anything, we're taking the opposite. But
Okay.
subtract, I always learn the rule for subtraction is you don't. You change it into adding the opposite. And are you folks up to one more activity, or should we leave that last activity and the rest of chapter 5 for next class?
I don't know about anybody else, but I don't feel too good, but everybody else could be fine. So whatever everybody else want to do, I'm a team player. I'll do what you guys do.
What do you folks think? Shall we call it a day early, or should we do one more activity? Courtney, the weight's on your shoulder. What do you think?
Wait till next week.
Wait till next week. Naomi's spoken. Dorothea's spoken. What about everybody else?
Wait till next week.
Wait till next week. Okay, you guys have
I
to
wait till
promise me something. Because this was like a light week note-wise, although I think conceptually some of what we did with the Euclidean method and the product method for greatest common divisor and least common multiple is a little bit more rigorous. Promise me that by next week, you will have looked at and almost completed all of chapter 4 homework, so that if you have any questions at all, we'll hammer them out at the beginning of next class, and then we'll look at chapter 5 notes. Sound like a plan?
Yep.
Do you like doing the activities or not? Yeah, okay, all right. And before we make it a day, I know that there were 1 or 2 people that I had to let into class a little bit late. Who is here now that was not here when I first took attendance? Tiara? I think you came in late. Are you still there, hon? Tiara? Anybody else come in late? I think that's it. Okay, all right. Have a great week, you folks. If you have any questions, shoot me an email. If you have any questions, stop by my office hour. I will try to get those tests graded before the end of the day Wednesday. But again, over the weekend, besides your test, I gave 4 other tests. So I promise I'll never time things that badly ever again. So have a great week. All right. Bye.
Bye.
Bye-bye.